The Claisen condensation can be intramolecular. Look what happens if you have a diester with the right number of carbons between them. Here we can form the enolate, and it can do nucleophilic attack on this carbonyl. Then the ethoxide can be lost as a leaving group. Notice we form a 1, 2, 3, 4, 5, 6-membered ring, which is favorable. Remember, anytime you can form a 5 or a 6-membered ring, it will. So this carbon is right here. Notice this carbonyl right here. When we have a Claisen condensation that occurs to make a ring like this, an intermolecular condensation, we call it the Dieckmann cyclization. So you go ahead and try it. Can you do the product of the Claisen condensation product, the Dieckmann cyclization of diethyl hexane dioate? So here is diethyl hexane dioate. What carbon is going to be deprotonated? As long as you pick an alpha carbon, it doesn't matter. This is a symmetrical compound. Well, I have this lined up so it's easy to see the ring closure. So either this or this, they're identical. We're going to have this do nucleophilic attack here and lose this ethoxide. Here's the product. Notice we made a 5-membered ring, so it goes ahead. You would not make a 4 or a 3, or of course not a 2. That's not impossible. And you won't make a 7-membered ring usually, but you will make 5 and 6 naturally. So you go ahead and determine what is the product of a Dieckmann cyclization of diethyl heptane dioate followed by alkylation with allobromide, then hydrolysis and decarboxylation. Well, there's a lot of steps here. Let's just take it one step at a time. Here is the heptane dioate. This carbon is the alpha carbon and so can do ring closure, and we get a 6-membered ring. This can then be deprotonated. Ethoxide strong enough. You don't even have to rinse with water or acid here. You could just take the anion and then drip in the allobromide, and what will happen? We'll end up getting this compound. If we hydrolyze this ester and heat, we're going to decarboxylate, and we end up getting this adduct. We have something called a Michael addition. A Michael addition is building on two things that you understand. When you have a conjugated carbonyl, it will add on the beta carbon anything that is a soft nucleophile where there's not a lot of charge concentration. If I have a 1,3 dicarbonyl and I treat with sodium ethoxide, it completely deprotonates it, but this negative charge is delocalized across all these carbonyls. That's why it's so acidic. Well, that makes it softer. Soft carbonyls will soft nucleophiles will add to the beta carbon of an alpha-beta unsaturated carbonyl. It adds here, and then when we wash with water, we protonate here. And that's called a Michael addition. So go ahead and figure out what would be the product of this Michael addition. Well, deprotonation right here would cause this to do nucleophilic attack here, and then washing with water would protonate here. The product that you get is this. Notice this is this unsaturated carbonyl. This is these carbons in the dicarbonyl compound right there. There's something called a Stork reaction, which is similar to the Michael addition, except what we have as the nucleophile is not a dicarbonyl enolate, but we have an enamine, which acts like an enol. So you remember how we formed enamines? We took a secondary amine and mixed it with a carbonyl compound, and that gave us an enamine. This enamine is nucleophilic. And enolate is nucleophilic because we've got negative charge right here. And but this is rather basic. Now, if you have two carbonyls, that spreads out the charge, so it's not quite as basic, and so it does 1,4 addition. But this is even less basic. And how is this a nucleophile? Look at the resonance structure, where it puts lots of negative charge on this carbon. That carbon has a large del negative. Now this can do 1,4 attack on an an unsaturated carbonyl. Here's an example. Cyclohexanone mixed with pyrrolidine gives you an enamine. That gives you nucleophilic attack. Here we get nucleophilic attack on the unsaturated carbonyl. And we've got negative charge here now. Now when we wash with water, what happens? We get protonation here. But we get another thing that happens. What happens is this gets cleaved back to the ketone. We end up with a 1,5 dicarbonyl compound. There's something called a Robinson annulation. An annulation means ring formation. And what happens in the Robinson annulation is we use two things you already know. A Michael reaction followed by an aldol condensation. So let's see how this works. If I treat this dicarbonyl compound with sodium ethoxide, I'm going to deprotonate here, and that's going to do 1,4 addition on this unsaturated carbonyl. That gives me this after protonation. The sodium ethoxide, though, can deprotonate here, and you can get addition to this carbonyl and then loss of water. If that happens, we get this unsaturated carbonyl in a ring form. And so this reaction, when you have a go, is called the Robinson annulation. It's just using two reactions you already know. Now, I want you to think about this question. In a mixed Claisen reaction of cyclopentanone with ethyl formate, you first mix the two carbonyl components and then add sodium ethoxide instead of mixing sodium ethoxide with cyclopentanone and then adding ethyl formate. Why is it you do that? Well, if you were to mix sodium ethoxide with cyclopentanone and it's just mixed by itself, you're going to have an aldol condensation occur because sodium ethoxide does not completely deprotonate cyclopentanone. You'll have cyclopentanone and the cyclopentanone enolate form, and they're going to end up doing the aldol condensation. If you have ethyl formate present, what will happen is that as the enolate of this forms, you're going to start having the Claisen condensation occur on the ethyl formate, and it will accumulate the Claisen condensation product, and you are not going to have reversal of that reaction that allows the aldol condensation to occur. So what is the reason that that benzaldehyde does not form an aldol condensation product? Well, you can read through all of these, but the reason is because there is no alpha proton here. There's no alpha proton on either side of the carbonyl. So the molecule doesn't have any hydrogens alpha to the carbonyl group, so no aldol condensation is possible. What's the product of this reaction? Ethanol is just a solvent here. So if I look, sodium hydroxide, the only thing possible for this to undergo with sodium hydroxide would be the aldol condensation. So let's look for the aldol condensation. These are all ketols. So let's go ahead and look and see which one would be the correct ketol for an aldol condensation. I'm going to be looking for this compound with an adduct. All of these have that compound there. But what we're going to do now is chop this off. Well, we're going to be showing the aldol condensation product before dehydration. So what you're going to have attached here is going to be a carbon that would have an alcohol right there. So a carbon here with an alcohol attached. So this has a carbon with an alcohol, but there has to be two ethyl groups attached, so that one doesn't work. If I look at this, there's a carbon with an alcohol, but there aren't two ethyl groups. See, we're going to have two ethyls and then a carbon with an alcohol attached to right here. No, two ethyls, you have the wrong arrangement over here. Again, a carbon with an alcohol, but there's only one ethyl group. You don't even have, it has to be on the beta carbon that you would have the hydroxy group, so this is way off. And if I look at this one looks like the aldol condensation. You can see dehydration could occur here. This and this are those two groups. Here's the ketone as a nucleophile. This is the enolate carbon, and this would have been the carbonyl. So this is the correct product. What will give this aldol product? Well, if I look at this, let's take it apart. You would have to have the adduct forming through this carbon bond. So we have to have a carbonyl here, and then here's our enolate would be there. This is basically the two of the same compounds. So I'm going to have this compound like that, and then this compound with it not being added. So it has to be this compound right there.